right, guys, so help me out. What are you getting for the error here? I didn't even do it yet. Anybody get anything? Otherwise, what the hell have you been doing? Say again?
0.037.
Yeah, 0.037. So if you do 2.05 times the square root of all this, you should get 0.036649, and you can round that to 0.037. So double check that, make sure you get that. And again, normally the problem is you have one of those older calculators and you close a parenthesis too soon, which means you come out of the square root, which is going to be a different problem than what you really want. And now to get the interval, I just subtract this from this. Oh God, 627? No, that can't be right, Jeff. 6.7.
6.7.
Thank you. And then 0.741?
Yeah.
Okay, I can add 37 to 4. Good job, Jeff. So that's a nice little quick little way. Here's the interval. That's the whole point, is to find the confidence interval, but then we have to interpret it. Because you have crazy-ass Jeff that wants you to realize statistics is more than just numbers. Statistics is the interpretation of those numbers. That's real stats. This is grunt work, right? Real stats is interpreting. What the hell does this mean? We are 96% confident that the interval 66.7 to 74.1% does what? Contains a true percentage. What was this? All
People that vote to registered voters.
registered voters that voted in the last election. All registered voters. So this is what's called inferential statistics, because I am inferring something about the entire population from what I see in my sample. Descriptive stats is just, here's what I see in my sample, I'm going to describe it for you. Inferential is going one step further and saying, oh, well, this, I know something about the population. And what's the chances that we're wrong, that we didn't catch the real percentage? How possible is it that I'm wrong? You can do it. How sure are we that we're right? All right, so how possible is it that I'm wrong? 4%. All right. And that's pretty good. That's better than average for me. I have a 4% chance of being wrong. Well, yeah, that's a good day. All right, so let's look at number 2. If you haven't started it yet, it's fine. So we did a problem like number 2 for means. And it's the same idea. I called it a feasibility study. If the sample size you need to be within so much is 1 million, and it's just you and your friend Sam, you're not going to go talk to 1 million people. I'm sorry. You're not going to do it. So it's how feasible is it to do this? Now with the sample size of 652, how close did we get? How big was our margin of error? It was 3.7%, right? So if I wanted to have this get smaller, if I wanted to be closer to it, I'd have to make this go up. I mean, day one, that made sense. The bigger my sample, the more sure I am about the results. It's beautiful, holy shit. That's all it's saying in pure mathematical form. It's awesome. All right, so let's look at, everybody cool with that? Everybody got what they want from that? More than you wanted? Okay. That's what I do. I give you more than you wanted. Okay, so number 2 is really built the same way we built it last time. Just to show you some of the algebra here, the error in this statement is this piece here, right? I'm trying to solve for n.
Yeah.
Can anybody identify the worst thing about this? equation that I have to work with? Where is n? There's two bad things about n. Where is it? Where is n? I want to solve for n. It always sucks when the variable I'm trying to solve for is two things. It's on the bottom, and it's inside of a square root. So how do I solve for it is basically take care of those problems. Let me first square everything. What's that going to do for me? It's going to kill my square root, right? Square. So we got e squared equals z squared times the square kills the square root. That's automatically better. My n is not stuck inside a square root. It is still stuck on the bottom, but I don't know if you guys remember the shortcut. If this equals that divided by this, then shoo-boop. If I divide by e squared and multiply by n, I can just boop. Boop. It's an awesome fact of numbers. It's not even an algebra fact. It is a number fact. If 10 divided by 5 is 2, then 10 divided by 2 is 5. Shoo-boop. Right? You don't have to make that sound. Oh, if you did, that'd be awesome. So now, I can see how large of a sample I will need to be within so much. Now here's the thing. Where do p hat and q hat come from? Where do they come from? What does the hat mean? Where do they come from? Good. P is success probability, Q is failure probability. Where do they come from? Sample. Have I taken a sample yet in number 2? No. Shit. So, the classroom this way that has people in it, what percentage of them are women? Do you know? What's a really good guess? 50%, right? So if I do not know what p hat and q hat are because I haven't taken a sample yet, I assume they're 0.5 each. Now this is kind of awesome. I'm going to say this, what I said to these guys earlier. If there is something I don't know in that equation, like p hat and q hat, and I have to guess for it, the answer should be more conservative. It should punish me in a way for not knowing this. So if I make p and q 0.5, n is the biggest it could be. Why is that a punishment? Because that's the sample size I have to take. Oh, you don't know p hat and q hat? Well, let's make your n a little bigger. It's like, what's this nice little n? I need to make it bigger. All right, sorry. Just pay me a little money, no problem. So this problem, did I say, please, dear God? Yes, I did. P hat and Q hat are each 0.5. We know that. What's E going to be in number 2?
0.03.
Yeah, I want to be within 3%. That within is a magic word for error. Because error is how much you're within. So let's see. I get n equals, I know E is 0.03. I got to square it. That's another thing people forget. I know P hat and Q hat I'm assuming are 0.5 because I have no freaking clue. What's Z going to be?
2.5.
Yeah. I'm just waiting to see if anybody else agrees. It's that little asterisk dude, right? If you do, or, I'm sorry, you look at the little baby charts, even better. 2.575? Today we'll learn it's actually 2.576, but that's a good enough estimation for now. And then you throw all that shit in there. You see how big your sample has to be in order to do that. I might be off by a factor of 10. I think it's 7 something around. 700 or something. Don't worry. I'm trying to do it in my head, so just look at all the 0.03s and shit up there. I'm not, I don't know. Times 0.5 squared divided by 0.03 squared. God, Lord, I'm off. Did I forget to multiply by something? Yeah. 1487.77, right? I'm okay with being wrong this early. What did I forget to do? I'll let it go. Oh, I didn't square this. Thank you. I'm kind of happy I made that mistake. That's an even, you sure? Yeah. There, see, you know. Yeah, it's really easy if we get those poor little squares, dudes. So what do you get when you do that? 38, 31? Oh, what did I do? Let's try this again, Jeff. I'm having a really weird morning. There's what happened. I put a 2 instead of a square on that. That's good. 1841?
Yeah.
Yeah, Jeff. 1841 point something or other. You always round this up. We had the discussion last time. 1842. Is that when Columbus sailed the ocean blue? Was it 1492? It was in 1800, Jeff. Good Lord, man. All right. What did I want to say right now? I forgot. Oh, so that, if I don't know anything, I'm going to have to take at least that large of a sample to be within 3%. Part B shows why we normally do preliminary studies. You all have heard of this. It's a preliminary study. So you do a little preliminary study to help you really see what n has to be. So if I just like to say the word preliminary. If I do a preliminary study and I get, what did I say? 31 out of 42, right? What's 31 divided by 42? 738? So what's Q hat?
1 minus 0.262.
So here I had to assume they were 0.5 because I had no idea. And that's my best guess. And mathematically it makes n the biggest to punish me for not knowing something. Over here I know shit now. I did a little preliminary study. So now I can plug those in instead. So it's the same formula. I still want to be 99% confident, right? I can now just put in here more specific information now that I did this preliminary study. So it should be a decent amount less than this. I think it's going to still be in the thousands. Yeah. You guys getting anything for that? Yeah, I get 1424 point, doesn't matter, you round up to 1425. So over 400 less people I'd have to talk to, right? That's a decent trade-off. In fact, now be careful about the way I word this. I'm not going to let this be a trick question. If you stop there, you're fine. But notice I say how many more people. How many people did I talk to already for this problem?
More than.
I talked to 42. I need a total of 1425. So how many more people would I need to talk to? 13 who?
83.
Yeah, their point. What a freaky morning you have. 1383. I'm not meaning that to be a trick question. If you forget to do the minus thing, that's fine. But that's really what you would do. I took preliminary study. I already talked to some people. Now I can figure out how many more people I need to talk to be within whatever percent my boss wants me to be. I want you to be within 3%, Johnson. It's always Johnson. Let's do another one of those. Any questions on that stuff there? It's a beautiful parallel between what we did with the means. I can find a confidence interval. I can figure out how big of a sample I need to be within so much. I do the same thing with percentages. And now it makes complete sense. If you see a news story saying 44% are going to vote for Prop 6 and 42% are going to vote against it, and at the bottom it says, plus or minus 4%. You're like, I know how to calculate that shit. Check the news, see if they did it right. If you don't see that plus or minus, then screw them people. They don't know how stats work. I can't trust them. You have to report that. Too many people look at that and they say, well, why would I even vote? My guy's going to lose. There's an error margin, right? If it's 44 to 42 plus or minus 4, it could be totally the other way around. That's what so sucks with people not understanding statistics. This has been demonstrated to happen. People see the poll and they go, why would I even go? It ain't got a chance. Well, now it definitely don't have a chance. Shit. That's why it's so important for everybody to have their own poll so they can kind of work it so it makes it sound one way or the other, because they know if they can make enough of them sound like their person's going to win or their thing's going to win, they can maybe make some of the people stay home and it will happen. If you believe that that won't happen because people are good, wake the shit up. Fudge. All right. So let's do one more of these just to really make sure we got this down. And then we have one new idea to discuss today, and then we'll head out. Okay, so I asked 37 people. Yeah, I'll throw myself in the mix. 38. Let's make it 38. How many of you guys have, what do you guys want to know? I was going to say traveled outside the U.S. Is that interesting enough by itself? Or how many of you guys have ever traveled outside the United States? Some of you guys are like, I traveled here, so yes. All right, wait a minute. Oh, shit. Raise them high. Holy shit. Let me see. A lot of us. It's awesome. Holy crap. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Oh, plus me. Yay. 28 have traveled outside the U.S. I am not trying to make you feel bad if you haven't. All right? What was I? I was 25 before I ever made it further west than Roanoke, Virginia. I was always on the eastern seaboard. And then it was 2001, right before 9/11. I took a trip to France and then went all around Europe. And my round trip ticket to France was $400. And I could bring my own water bottle. Didn't have to take my freaking shoes off, keep my belt on. My friend can come to the gate and say, bye, Jeff. It was a different time. All right. And like, that was never true. And 8-track tapes never existed. All right, so let's see. So what can I calculate from this? Even right off the bat, I can just calculate what? P hat? What is it, sorry?
0.737.
737? That's awesome. 737. Maybe you guys flew in a 737. All right, so maybe it's just me that likes that. And then what's Q hat going to be then?
263.
263, I like it. Okay. So almost 74% of the people in here. Robert, you were here when I did this, right? When I asked if you had been out of the United States? Don't worry. If you weren't, you could be an observer. Sorry. Poor Robert, I'm sorry. I didn't mean to call you. All right. So you can calculate this stuff. I haven't asked the question here, right? I haven't said find the whatever conference. You can calculate this stuff. This is descriptive statistics. Because I'm describing what I see. How sure am I that my sample percentage is this? 100%. Because I see it. What is it that I'm not sure about is the true percentage, let's say, of all Grossmont students. Now, would you guys be a good sample? We did this the first day. So this is going to suck, right? We're not going to publish these findings, right? It's going to suck bad. But oh well, too bad for us. So I want to get a feel for the true percentage of all Grossmont students who have traveled outside the U.S. You guys are a bad sample, but too bad for us. So I want to create the 98% confidence interval for the true percentage who have traveled outside the U.S. So take a minute and try to figure out, can you figure out what the Z would be for that? And why am I allowed to use Z-scores? What do I check? Check for normality. There's another one of my favorite words, normality. So malady is a bad thing. So normality is a good thing, I guess. How do you check? What do you look at? N, P hat, and Q hat. What is NP hat? You don't have to do any work. It's 28. The number of successes. Now you could do the work and you get 27 point whatever, something like that. But it's 28. And then what's NQ hat? The rest. 10. And again, do the work. Do the work. What do you get if you do 38 times 0.737? That's N times P hat. What do you get with 38 times this?
28.006.
11, which is frickin' 28, right? Why isn't it exactly 28? Because we rounded to 737. What's on the bottom of this? 38. So when you multiply this by 38, you got to get frickin' 28. And again, it doesn't matter if you don't get that. It's not a huge shortcut, but you can just see. If this was 4, screw that problem. It's going to be less than 5, right? So these are both greater than 5. That's all right. You're being hopeful. We don't have to do it yet. About what? Sorry. No. Okay, just. This is something you have to memorize, exactly like you have to memorize n greater than 30. If I say n greater than 30, is everybody cool with that? What does n greater than 30 mean? For a means problem, it's normal enough. What do I check for an NPQ problem, or percentages problem? I check this. That's all. Don't get lost in the weeds on how to get this number. If you don't remember just to look, you just do n times p hat. And you'll get roughly what you're supposed to get. All right, I like it. Now, see if you can figure out what this is, because I know I'm allowed to use z-score chart to get z-scores. Figure out what this z-score would be.
Yeah, that one is cheap. That's why I was doing that one. Yeah. That's closer.
What do you get for the z-score?
Negative 2.33.
Why doesn't the negative matter? I don't want that to be a tripping point. Because it's built in there already. It's in there. Like ragu, no? Okay. That's why there's a plus or minus. How many sides are there to a confidence interval? 2. Minus gets this side, plus gets that side. Plus or minus isn't there, so you really just care about the number, 2.3 feet. The negative is because you looked this one up first. Whoop-de-doo. Don't put the negative in there and get all confused when you put it in your calculator. Now try to do this. You got everything you need to do that. See how far you can get. Construct that confidence interval. I'm curious where you guys have been. That's like the biggest percentage I've ever gotten, which is good. The more of us that get out of the States, the better the States will be. Period. error you're getting should be kind of big because your sample size is small. What are you guys getting for the error?
166.
I like 0.166. If you want to go more places, that's fine, but you only have to go 3. That makes sense. That is big. It's 16% off. It's big for 2 reasons. The z-score was kind of big, and my sample is really small. So those together, z-score, if I want to be 98%, I've got to go further out, and my uncertainty is larger because I have such a small sample. So let's see, what interval do you get when you add and subtract there? Oh, scheisse. I don't trust myself today.
57
Oh,
06.
571?
Yeah. 90.
Shoot. I didn't get to the point where it carried a 1 on that. All right. That's kind of pathetic. If somebody told you, yeah, I think about somewhere between 57 and 90%. It's like, so you don't know. That's what you're saying. You don't know. At least the one good thing about this, what was this all about? Would you say that it's likely that a majority of students at Grossmont have traveled outside the U.S.? Pretend like you guys are a good sample. Yes, because this confidence interval shows that it's definitely, within the error, it's definitely more than 50%. So this is still evidence of something like that. Can you say that more than half? Yeah, it's evidence. Is it proof? Oh, hell no. Because there's a chance this is wrong. Always. But that's why I love statistics. It's so honest. Oh, yeah, do the math. Get your little numbers. Round it as much as you want to, but there's always a chance you're wrong. Not because you did something wrong, because that's life. Right? Okay, so if you're learning statistics to hope to God you can play the stock market or do better at poker, you will be able to, but not each individual time. Poker players have to play for the long run. Lose 7, win 1. You get millions of dollars. You're good to lose the next 7, shit, and then win the 1, right? That's the whole you got to have money to make money thing. So how do I say this? We are
57.
we're 98% confident that the interval. Now you got it. 57.1% to 90.3% contains true percentage of Grossmont students as traveled. Blah 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 blah. Right. So you always have to reference the physical situation. Don't just put dots. I can because I'm the teacher. Nah. You put I got time. So confidence intervals are not difficult. They're bodacious. And we have 2 formulas so far for confidence intervals. We're going to learn one more right now, and then we're going to call it a day, because that's a lot. So, all right. Normally, we know what we've done so far. Let me put this up here. Has everybody got what they want from this here? Okay. There's always this girl I would say, wait, right there. Like, oh, come on. So here's the first confidence interval formula we created. And at that time, I mentioned something that wasn't really true to form. Sometimes we know this thing, but most of the time, I'm not going to know shit going in. So sometimes we know the population standard deviation. But most of the time, we're going to go into a situation like I'm going to go test water levels to see if there are too many toxins and it's affecting the local people. So when I go in, do I have any idea what the standard deviation of toxicity is? I don't have a freaking clue. I'm going to see in my sample, I'm not going to know this. And we already know. When I don't know the real standard deviation, I'm a little screwed. Oh shit. So what would happen with my confidence interval? So if I did know sigma, and it led to a confidence interval of like 11 to 13. Let's just pretend we do all the work, and we get 11 to 13. If I did not know sigma, if I only knew S, remember what S is. What's S? Sample standard deviation, right? Greek letter, population standard deviation, everything's great. Sample standard deviation, oh shit. What should happen to the confidence interval? Should it be bigger or smaller? Should it be wider or narrower? How do I cover my ass for not knowing something that I need to know? Should I make it bigger or smaller? I love the idea, and some of you guys might not be able to handle the word ass. I love the people that can't handle the word ass. But how do you cover your ass? Well, you got to make a little bit bigger towel, right, to cover your ass. So if I know this, I'm going to get a constant. If I don't know this, it should lead to a larger interval to cover my ass for not knowing. So if I wanted to catch a fish and I didn't know how far it swam, I'm going to have to use a bigger net. You're going to need a bigger net. No. So maybe that would lead to 10 to 14 or something crazy. I don't know. But the idea is it's going to make it wider. Now, what really controls directly the width of an interval? Sure, but let's say the sample size is the same. I just, in one situation I know this, but the other situation only that. So it's going to be this. It's going to be this. The C's. All right, I want this to make complete, scary amounts of sense. So let's do one where I know sigma, and then I want to do it again where I don't know sigma and ask you what should happen. So let's say I know, we know X bar is 11, N is 32, sigma is 4, and if I make a 95% confidence interval, that's a z-score of 1.96. Some of you guys might remember that. Don't be scared if you start remembering it. Okay, so I just gave you everything, just to do this really quickly. So this confidence interval would be 11, give or take, 1.96 of these. So 11, give or take. I'm going to do this a little bit quickly, just because we just did this. I think it's 1.386. So we get 9.614 up to 12.386, if I did that right in my head. I'm sure you guys will tell me if I didn't. So, I am allowed to use z-scores if I have a normal distribution of means, which I do because that's bigger than 30, and I know sigma. When I don't know sigma, when I only know S, I have to change something. I have to make my interval bigger. So what's going to change is I'm not going to be able to use this number. I want to use a number that's a little bigger than this. In fact, what has to happen to my sample so that I'm more sure about S? What's going to make S get closer to sigma if my sample is really big?
smaller is equal.
So the number I use here, the number I use here instead to cover my ass for not knowing sigma is going to be dependent on how big my sample is. If I got a really small sample, it's going to be a lot bigger than 1.96. Wow, it's going to be crazy because it's like, you don't know shit. But my sample is big, 100, 3,000 or something. It's going to be closer and closer to 1.96. It's like you don't need me as much. You're getting more and more sure about your stuff. So with that in mind, all right. Let me give you this. It's always interesting when you're teaching. You're like, what order do I want to tell people shit? Here, let me give you this. Oh, you're going to be so excited. Here's a different chart. We call these new scores, we call them T-scores. And it actually it was developed by a guy that worked at the Guinness Brewery. Brewery is another good word. I'm not a drunk officer, I just can't say brewery. Anybody like Guinness at all? Somewhat, it helps you get through physics, that's for sure. We go drink a pint down with our physics teacher after class. I was like, oh, this is how physics makes sense. Get yourself a little inebriated. Anyway, there's a guy that worked at Guinness, and he did some studies, and he wanted to publish it, but Guinness had a contract he had to sign that said, anything you figure out, we're going to use for ourselves, So he published it under a pseudonym, anonymously. He called himself Student, and he published his findings. So now we call it the Student T distribution. His name was actually William Gossett. I want him to get credit. I don't know if you guys are all interested. I'm such a weird guy. I read big books about statistics history. I do. This is how I enjoy my Saturday nights. As I sit, no, it's not that bad, but I'm reading about Guinness. Oh, that should be good. But this is really kind of cool. It was that's the story. That's where this came from. So here's how this works. First thing I want to get into is, do you remember, just to explain there's some words on here that don't make sense at the moment. There's a lot of shit that don't make sense on this here for right now. First thing I want to explain is degrees of freedom. You guys see that? Degrees of freedom. It doesn't say sample size, it says degrees of freedom, but they are directly related. Do you guys remember when we did sigma, we did this? Do you remember doing this? Over n? What was the difference here? Oh, that's not squared. What was the difference here? It was over what? Not n, it was over.
Yes.
Remember that?
Yeah.
Okay. Here's a little more explanation where that comes from. Now, this is an entire side discussion just about this. You guys with me? And it's going to end up, it's just freaking n minus 1. So my sample is 32. What are you going to look up? 31. Ooh, that's the end result. So you're like, don't even do what you're about to do, Jeff. I can't stop myself. If I have 4 numbers, let's say 3 numbers, and I know the average of them is 10. Do you know anything about any individual number? If 3 numbers average to be 10, do you know anything about each number? Could one of them be 8? Of course. Could one of them be negative 1800? Of course. Okay, I want you to realize this. What do 3 numbers have to add to be so that their average is 10? How do you find the average of 3 numbers? You add them up and divide by 3.
Yeah.
So what's the sum have to be so that results in 10? What do you divide 3 by to get 10? What do you divide 30? What do you divide by 3 to get 10? 30. So this is neat. If you know that 3 numbers average to be 10, you don't know shit about the numbers individually, but you know together they have to add to be 30. So I can I can totally make this up. I can say that's 8, and that's 15. And now I have to get serious, right? I can't just make up shit. So that last one has to be what in this case? 7. So that they add up to be 30. Do you guys see that? So how many degrees of freedom do I have? Do I have 3 degrees of freedom, meaning do I have 3 things I could just totally make up?
No.
How many degrees of freedom I have? 2.
2.
Ah, that's why n minus 1 is called degrees of freedom. You can take my freedom. All right, so let's try this again. What would the t-score be for this situation? All right, there's another piece of that I have to explain. At least now we know what the degrees of freedom would be. For this problem, what would the degrees of freedom be?
51.
So at least you know which row to look at now, right? Okay. Now, the top, let me at least get this guy woken up. The top, do you see how it's got 2 rows? And it says area and 1 tail on the top?
Yeah.
Boop, boop, doop, doop, boop.
No.
Go boop. Go boop. Okay. Oh, I don't know. Oh, there you go. Okay. All right, let's do this. Watch, watch, watch. Look at the, if I have a 95% confidence interval, how much is in each tail? You see why we call those tails? Don't they look like tails? So, yeah, 95%. There's going to be 5% total in 2 tails or 2.5% in 1 tail. Is everybody cool with that? So look at the area in 1 tail. Do you see how 2.5% is right in the middle?
Yeah.
And do you see right below it that corresponds to 5% in 2 tails? Doesn't that make freaking sense? If there's 5% in 2 tails, how much in 1 tail? Half of that. So it doesn't matter if you look at it as 1 or 2 tails, you will always end up in the same column. Now what z-score did we get for that one? We got 1.96, right?
Yeah.
If you go all the way to the bottom of that column, what number do you see? 1.9 frickin' 6. Why is that? Look over there. What's the degrees of freedom for that very last entry? I think you gotta love that shit. Large. The reason they just put the word large is it depends on how precise you have to be. You don't have to be that precise, just use a frickin' z-score. But if you have to be really precise, you're gonna use technology to figure out the t-score 1.9700, you know. But do you see how, if my sample gets really small, look what happens to the t-scores? Go up to a sample size of 2, which would be degrees of freedom of 1. It would be, the t-score would be 12.70 frickin' 6. If I only took 2 things, how sure am I about the real standard deviation? Not at all. So that's like saying, it's going, shit, you don't know shit, you gotta go 12 steps. Screw you. Right? Okay, I like it, I like it. But the bigger my sample gets, the smaller the t-score gets, the less I have to cover my ass, because the more I know.
Yeah.
So as my sample size gets bigger, which means degrees of freedom are getting bigger, do you see how my t-score is getting smaller? And in fact, when the sample gets large, it becomes a z-score. So here we go. All right, I'm going to say this so many times. This is a t-score chart. This is a t-score chart. But at the bottom of this sucker are z-scores. Because what do t-scores do? They become z-scores when my sample gets really big or large. Let's look at C. Does anything else look familiar? We did a 99% thing earlier. We got 2.575. Look, 2.576 in that first column. Right? 1.645. Isn't that look familiar? And 2.326. Didn't we just do one that was 2.33? We're 98%. 90% has how much in 2 tails? 90% inside, how much total outside? 2%. Careful. And if I look at this, isn't that the 2% in 2 tails column? Okay. Okay. So let's do this. Let me put this up here so you guys can see what I'm talking about. Oh man, let's see. Just read my mind as to what I need. Projector. Does somebody turn off? I think it's that first light closer to me. Oh, you're not even playing, are you? Are you? Whoa.
Oh, yes.
You went for it. Okay. Just that first one, I think. Just the first one, yeah. Just that one. Do it. I don't know. So turn the other one on. Or turn them both off. Turn them both off. Thank you, I'm sorry. So it must be, anyway, screw it. We'll figure it out. Oh, good. All right. Cooperate. Cooperate. You just suck. You need to go somewhere else. Send you guys away. Woo! What? Where are you? Boy. Good Lord. All right. Whew. So help me out. Which column would I go to if I needed to make a 90% confidence interval? Which column would I go to? 90% confidence interval. Doesn't matter which way you look at it. If there's 90% inside, there's how much total outside? How much total outside? 10%. 10% in two tails. How much would be in one tail then? 5. See, 5% in one tail. Which column am I in either way? This one, the fourth one, right?
Yeah.
So it doesn't matter which way you look at it. Now, confidence intervals always makes two tails. So you can always go here if you think about, if you want 95%, you're going to look at 5% here. Because if they're 95 in, there must be 5% total outside. The next chapter, we're going to be doing tests like, I think the mean is bigger. And then it's going to be one tail test. So that's, in the next chapter, the one and the two tail are going to make a lot more sense why they're both there. So if I wanted a 90% confidence interval, I would look here in this column. Right? So let's see if we can get it. So if I knew S, and I know it's, N is, what do you got, Jeff? 81. Can you figure out what the t-score would be? Don't say anything out loud. What would the t-score be for this situation? So again, I know I'm looking in this column here, right?
Yeah.
What's my degrees of freedom? I cannot say that any other way. What's my degrees of freedom? 80. Does it have an 80 on it? Yes. Oh, crap. So here I am. If I just look at the paper, it'd be better. There we go, Jeff. Degrees of freedom is 80, so I get a t-score of 1.664. If I knew sigma, I would use 1.645, but since I don't know sigma, it's going to make it a little bigger to cover my ass for not knowing something. Such a beautiful idea. Somebody is like, whatever, just tell me where to put stuff. Please make me stop. Okay, all right, so let me give you this. I like this little handout. At the top, it's got what I call the lightning round. Oh, by the way, I don't know if you picked up on this. In order to use a T or a Z, you have to have a normal distribution that you're working on. So if N is 11, it better say it's freaking normal somewhere, or else you can't do shit. Z or T, I don't care. Right? So here we go. Try this handout. Oh, crap. I lost count. Yeah. Well, I didn't. Not at the same time. That's what I mean. And you're still talking. I don't know. Bless you. Thank you. You've never seen Braveheart, you should.